Okay, so let's try a problem using Boyle's law. A bicycle tire has a volume of 1 liter of air at a pressure of 1 atmosphere. If the pressure is increased to 1.7 atmospheres, what would the volume be? So before we solve this problem, let's just think about this. We know that pressure and volume are an inverse relationship. So when one goes up, the other should go down. If one goes down, the other should go up. Let's look at what we're changing. What we're changing in the problem is we are starting at a pressure of 1 atmosphere and increasing to 1.7 atmospheres. So let's make a prediction. If we are increasing the pressure, what should the volume do? Well, if we look at what we wrote inside our foldable, if one goes up, the other goes down. So if the pressure is going up, then our volume should be going down. So we should end up with an answer that is less than 1 liter. All right. So our initial pressure, our P1, is 1 atmosphere. Our initial volume, our V1, is 1 liter. Our final pressure, our P2, is 1.7 atmospheres. The problem asks us to figure out what our final volume would be, our V2. So you'll notice I started by writing out every single number I know and figuring out, is it a pressure or a volume? Is it an initial or a final? Okay, then I'm going to take my equation, P1V1 equals P2V2. And I'm going to look for the element that I want to solve for. Here I'm trying to solve for V2. So I want V2 to be by itself. Well, in this equation, V2 is being multiplied by P2. The opposite of multiplying by P2 is to divide by P2. We are going to do that to both sides of the equation. When we do that, P2 over P2 will cancel, leaving us with V2 alone equal to P1 times V1 divided by P2. So this is the equation that we would put our numbers into and solve. Okay, so for P1, we put in the value of 1 atmosphere. For V1, we put in the value of 1 liter. And then for P2, we put in the value of 1.7 atmospheres. Now, if you look at your units, you have atmospheres over atmospheres. What can we do with that? We can cancel atmospheres right on out. It's not going to be in our answer. So the only unit we're left with is liters. Does liters make sense for volume? Yes, it does. So I'm going to do 1 times 1, and then I'm going to divide that by 1.7. This gets me 0.588239, blah, blah, blah. Okay? But we have just one significant digit here. So we're going to round this to 0.6, and the unit would be liters. Okay? Now, if you recall, we said that since the pressure was increasing, we would expect the volume to decrease, which it did. We went from a whole liter down to almost half, a little more than half, which makes sense because we almost, but not quite, doubled the pressure. Okay, so let's try a problem using Charles's law. Here it says, a balloon has a temperature of 200 Kelvin and a volume of 1.3 liters. If the balloon is heated until it bursts, it reaches a temperature of 239 Kelvin. What was the volume of the balloon before it burst? So we want to know how big did the balloon get before it popped? All right, so let's start by making a list of everything we know. It started with a temperature, T1, of 200 Kelvin. And an initial volume, V1, of 1.3 liters. We're going to heat this to a second temperature, your T2, of 239 Kelvin. We want to know the final volume of the balloon just before it burst at that temperature. All right, so we're going to use Charles's law, which is V1 over T1 equals V2 over T2. In this instance, we are solving for V2. So just like we did before, we want to isolate the variable that we want. This is going to be a little trickier though, because we got this messy little fraction. So we're going to do exactly what we did before and look at what the opposite operation is. So here in this equation, we're dividing V2 by T2. The opposite of dividing V2 by T2 is to multiply by T2. We're going to do that to both sides, making note that that means that it would be on the top of the fraction. So T2 over T2 on the right cancels out, leaving us with V2 by itself. So now we can go ahead and substitute in our values into this equation, T2 times V1 divided by T1, and that'll help us get our answer. So our T2 value was 239 Kelvin times our initial volume of 1.3 liters divided by our initial temperature, which was 200 Kelvin. Now, before we calculate this out using our calculator, let's look at our units. Remember, if something matches on the top and the bottom, we can cancel that out. I have Kelvin here and Kelvin here. So I can cancel out that unit Kelvin, and that's going to leave me with a unit liters. And again, that makes sense for volume. So we know we've done this right. So in my calculator, I'm going to take 239 times 1.3. Then I'm going to divide that by 200. This is going to get me 1.5535. Our maximum, we had 3 sig figs, 2 sig figs, and 3 sig figs. So remember, we always go with the least number of sig figs, which would be 2 sig figs. So I'm going to round my answer to 1.6, and my unit would be liters. Okay, so let's do a problem using Gay-Lussac's law. It says an aerosol can contains a gas at 3.1 atmospheres of pressure at room temperature, which is 23 degrees Celsius. The can will explode if it reaches a pressure greater than 4 atmospheres. The can is left in a hot garage that reaches 47 degrees Celsius. Will the can explode? Well, we're starting at a pressure and temperature that is known. It looks like we're going to increase the temperature, and we're trying to figure out if the can will explode. We know that the can will explode if the pressure gets greater than 4 atmospheres. So we need to figure out what our second pressure would be in order to see if it's more than 4 atmospheres. So let's have a look. Let's start by making a list of what we know. We're starting with an initial pressure, P1, of 3.1 atmospheres. And we're starting at room temperature, T1, but hold on a minute. This is in Celsius, and we need it to be in Kelvin. So we're going to do 23 plus 273.15. That's going to get us 296 Kelvin. Okay? Blah, blah, blah. We're not going to talk about this other pressure value because that's not part of the calculation. That's simply what we're going to compare our answer to answer their overall question. So then it says the can is left in a hot garage that reaches this temperature. So that's the temperature we're getting to. Is 47 degrees Celsius. Again, that has to be in Kelvin. So we're going to go to our calculator. We're going to do 47 plus 273.15. That's going to give us a value of 320 Kelvin. So we need to solve for the second pressure and compare it to this 4 atmospheres to determine whether or not the can will explode. So to do that, we're going to start with Gay-Lussac's law. P1 over T1 is equal to P2 over T2. In this case, we're solving for the P2. We're going to do this very much like we did with the Charles law one up there. We are dividing by T2. The opposite of dividing by T2 is to multiply by T2. So we're going to do that to both sides. Remember, that's going to put T2 on the top of our fraction on the left. So T2 over T2 cancels out, leaving us with P2 by itself equal to this equation right here. So now we can substitute in our values for T2, P1, and T1 and use that to solve for our final pressure. So our value for T2, be careful, that's T2, not T1. Our value for T2 was 320 Kelvin. We're going to multiply that by our initial pressure of 3.1 atmospheres. And then we are going to divide that by our initial temperature, which was 296 Kelvin. And again, if anything matches top and bottom, we can cancel it out. So we have Kelvin over Kelvin. So the Kelvin values, or the Kelvin unit cancels out, leaving us with atmospheres. And atmospheres is a unit for pressure. So we have this done right. So in our calculator, we're going to do 320 times 3.1. And then we're going to divide that by 296. Now, our least number of sig figs is 2 sig figs. So we're going to round our answer to 3.4 atmospheres. So the question was, will the can explode? Well, it only explodes if we get above 4 atmospheres. So we're not there. We're getting there. We should probably cool that can down pretty soon, but we're not to 4 atmospheres. So the answer to our question is no, it will not explode. We didn't reach the temperature and the pressure that is required to explode. Okay, so for this question, we've got a sample of gas is collected over water at 23 degrees Celsius and found to have a total pressure of 25.4 millimeters of mercury. If the partial pressure of water is equal to 21.1 millimeters of mercury at 23 degrees Celsius, what is the partial pressure of the gas alone? Now this looks a little scary because we got a whole bunch of numbers here, but it's actually an incredibly simple calculation. Because these temperatures, 23 degrees Celsius, 23 degrees Celsius, that's just the temperature value we need to look up this number, which they've already given us. So we don't actually need that value in order to do this calculation. We need the total pressure. We're going to call that PT. Our total pressure is 25.4 millimeters of mercury. And we also know the partial pressure of water is 21.1 millimeters of mercury. Now they didn't specify what gas it was, but they asked us to find the partial pressure of the gas, whatever it is that we collected. So we're going to call it the partial pressure of just gas, and that is what we want to find. Well, let's start with Dalton's law of partial pressures. We know that the total pressure is going to be equal to the partial pressure of water plus the partial pressure of the gas. Well, we don't know the partial pressure of the gas, but we do know the partial pressure of the water, and we do know the total pressure of the entire system. So what we can do is very similar to what we were doing before. We're solving for the pressure of the gas, which currently is being added to the pressure of water. Well, what is the opposite of adding the pressure of water? Be to subtract the pressure of the water. So we're going to subtract the pressure of water from both sides. Pressure of water minus pressure of water is going to be nothing. So 0 plus the pressure of the gas. So now we have the pressure of the gas by itself is equal to the total pressure minus the partial pressure of the water. So the total pressure was 25.4 millimeters of mercury. We're going to subtract from the total pressure the pressure of water, 21.1 millimeters of mercury. So 25.4 minus 21.1 gives us a partial pressure of the gas equal to 4.3 millimeters of mercury.